Hello, my name is Ansh Modi, and this is Lab 4. The purpose of this lab was to use the loop rule and the current conservation to predict the behavior of circuits containing resistors in series and parallel. We also learned to use multimeters to measure the actual values of conventional currents and potential differences in the circuits. And finally, examining the behavior of ohmic resistors and capacitors. So in our first experiment, we had it was a series circuit. The circuit consisted of two batteries and two resistors and two ammeters. I made a prediction for the value in both the ammeters based on the total resistance of the circuit, which was 47 plus 100, which gave 147 ohms. And the voltage was given two batteries with each 1.5 volts, so it was 3. And using V equals IR, I predicted that the ammeter should read 0.02 amps, and this was correct when I set out the experiment in our simulation. When an ammeter was reversed, the current was of the same magnitude but opposite sign. Next, I added a voltmeter in series, replacing one of the ammeters. This really resulted in the ammeter displaying 0 amps and the voltmeter displaying 3 volts. This is because the voltmeter has a very high resistance, and thus no current can flow through the circuit. Then I took the voltage measurements at various points shown in the graph by putting the ammeter in series. So, between the start and the end of the batteries, there were 3 volts. And then between the start and the resistor with 47 ohms, or resistor 1, there was negative 0.96 volts. And then finally, for the 100 ohm resistor, there was minus 2.04 volts. It should also be noted that the ammeter did not have any voltage in it. So the ammeter in this experiment read 0.02 amps, and the sum of the voltages added up to 0. So 3 minus 0.96 minus 2.04. This is the voltage graph plotted. So as you can see, it increases due to the battery and then decreases due to the resistors until it reaches 0, as it should. When we attach the voltmeter, we attach it in series to the circuit, and due to conservation of charge, the ammeter reads the same. The ammeter's reading is 0.06 when 1 is attached in series. This is because the current takes the path of least resistance, which is provided by the ammeter in series. We can use V equals IR to calculate the resistances of the components of the circuit. So, the 47 ohmic resistor had a resistance of 47, the 100 ohmic resistor had a resistance of 100, and the wire and the ammeter both had 100, 0. And this was the resistance were found using the voltages and the amps produced by our previous measurements. Next, we created a RC, resistor capacitor circuit. We created a circuit using a 10 ohm bulb, a 20 ohm bulb, which not together, separately, and then one 9 volt battery and one 200 millifarad capacitor. When we completed the circuit, we noticed that the light bulb lit up and then over a period of time dimmed out. This is because as the capacitor charges up, the current in the circuit decreases. Then we discharged the capacitor by removing the battery and directly connecting it to the light bulb in the circuit in a circuit similar situation where the light bulb lit up. When we discharged the capacitor through the light bulb, a similar situation happened when we were charging the capacitor. It lit up and then eventually dimmed out. The time I measured for the charging of the 10 Faraday, 10 bulb was 6.9 seconds, and for the 10 and discharging was 7.2 seconds. And this was due to a measurement error, but in reality these would be the same. And then the time I measured for charging for the 20 ohm bulb and discharging were both 8.7. Finally, the time-dependent voltage across the discharging capacitor, RC circuits. So I used a circuit similar to the one on the left, just with different values to calculate the time constant when a capacitor is discharged through an ohmic resistor. This was done by taking the voltages at various times as the capacitor discharged. In this experiment, we found the time constant of the capacitor discharging using a similar setup to the last circuit. I plotted a logarithmic graph of the voltage over the initial voltage and used Ln, the voltage over the initial voltage, equals negative time over RC, which is the time constant. Using a line of best fit, I got the slope of this graph, which was minus 0.292, and one of the inverse positive of this, which is 3.42. This means that the time constant is 3.42. Additional questions. So, what if we were to simulate this in real life and use an actual ammeter instead of an ideally simulated ammeter? How would it look different, and how would it affect the circuit? The real ammeter would have some degree of resistance, however small, which would have changed the results, as it would have drawn some voltage and decreased the current through the circuit. So maybe even like 0.01 amps, but it would be different, very slightly. What if you were doing this lab in real life and used the real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor will reach full charge? So, in real life, when using equipment rather than endlessly gaining ever so slightly more charge, the capacitor will eventually reach a stage where it will not gain any more charge, according to our equipment, because it would only be accurate or tell us to a couple of decimal places. So, the graph for the capacitor is logarithmic, so it eventually flattens out, but not in real. Like when we take actual measurements in real lab settings, this will not happen. We will not get these results. Thank you.